Good afternoon, sir.
Hello Pratap, am I audible?
Yes, sir.
So in last class, if you could remember, we covered a little bit of the equipotential surfaces. Right?
Yes.
Any doubt you have in that?
No.
Okay. So today I'll be discussing more about equipotential surfaces, and then we will discuss a relation between electric field and potential energy. Okay.
Okay.
So let me check. Yeah, these were the equipotential surfaces. The surfaces. Over which equipotential surface is a kind of a Gaussian surface over which at any point the potential remains same. Okay, the most important point is that potential energy in moving from one point to another point over any equipotential surfaces comes out to be zero. Is that clear?
Yes.
Okay. So today, so we'll be starting with topic relation between potential and electric field. Potential and electric field. This relation is very important because in further upcoming chapters like topics we'll be discussing this, we'll be using this as an application.
Okay.
Okay, so just assume that there's an random electric field like this. This is a very random electric field. Okay? This is a very random electric field, and we can say whatever it is shown, it is a path of electric field, like it is going from here to here. This is path of electric field. Okay. All right. Now what I want to do is I'll be taking a random positive charge and I will take it from this point. Let's say this is point A, and I will move it to point B. Here, I will move it to point B. I will take this charge from here to here in this electric field. Is it fine?
Yes.
Okay. So you know that if I'm taking this charge from point A to point B, the net work done by conservative. Who is this conservative? The electrostatic force, right? It will be equals to nothing. Final potential energy minus initial potential energy, is it?
Yes.
Okay. But how I should calculate this? Let's see. It will be nothing but what is energy? Energy is nothing but force into how much distance it has been done, right? So I can say the force. What is the force by electric field? It will be Q into electric field, right?
Yes.
And how much displacement it has covered? It has gone through something around dot ds. Clear?
Okay.
Okay, this is one thing, and we have to integrate this part. Now you know charge is constant thing, so I can take it outside, so it will become q e dot ds. Make sense? Now if you see carefully, what I have uf minus ui equals to q e dot ds. Can I rewrite the same thing as it is nothing but change in potential energy, right? So I will
Yes.
write it as this q. So what this becomes, isn't it du by dq, like du by q, which is, isn't it potential energy per unit charge?
Yes.
And what we call potential energy per unit charge? What is potential energy per unit charge?
Potential energy per unit charge.
Yeah, potential,
Uh,
right?
Electric potential.
Yeah, this electric potential, right?
Yeah.
So
Yes.
if you can see, I have figured out one relation between your V. Okay, it should be actually only D. Okay, here change was there, so you can write it like this. U and change comes out as potential. That's how. Okay. So if you see, I have given you one relation between V, E, and whatever the distance. So I can say it is the relation between electric field and potential. Okay. One more thing we have missed over here. In the formula with the minus W, there was a negative sign along it. So whole thing will have a negative.
Okay.
There should be no negative. Yeah. So this is it. Now, if you see, there's a negative sign at the end of the day, right?
Mm-hmm.
What does this mean? It means that if your if your E is increasing now, in
Yes.
that case your V is going to decrease. Clear?
Oh, okay.
Okay. Um, how we can say this? Let's take this as an example. You know, this is the path of electric field, right?
Yes.
Okay. So if I'm taking my charge from here to here, like if my charge is going from here to here, what does this mean? Like it's not increasing and decreasing. Basically, if I'm going in direction of electric field, my potential is decreasing. This is what, okay, the negative and positive here. It means it's related with the direction, not with the value.
Okay.
Clear?
Yes.
So if you see, if I'm going from here to here, what do you think, potential will increase or decrease?
Decrease.
Decrease, right? We can also think of, you know, if you see carefully the electric field, so it is in this direction. It means either there must be some positive charge at this side or there must be some negative charge this side. Only in this condition there will, like, because positive is there, then you can form this kind of electric field, or if negative is there, then you can form this kind of electric field, right?
Okay.
If I take any of the criteria, let's say I'll take first example with positive this side. In this case, I have positive charge here. Okay, so you know there's some potential in between, right? What is the potential? K Q, whatever it has charge, divided by R square. If I'm going from here to here, I am increasing my distance between this positive and this, right?
Yes.
So mean to say, if I'm increasing, basically I'm adding something, R dash. So I'm decreasing the potential, right? You can see this.
Yes.
Okay, this is something. Let's say take another example. If negative is this side, what does this mean? Due to negative, what will be the potential? It will be k q q naught divided by r square, and overall the thing is negative. If I'm going close to the negative charge, I am losing my potential, right?
Yes.
Like magnitude wise, you can say, okay, the value is decreasing, so overall the magnitude should increase. But if magnitude is increasing in negative sense, it means overall potential is decreasing. Decreasing potential mean to say bounded, right?
Okay.
Your state is getting towards bounded,
Okay.
and when positive charge was here, your state is getting more unbounded to lesser unbounded, right? Because positive are there, they're not bounded, but if you move little bit this side, your state of unboundedness increases. Okay,
Okay.
clear?
Yes.
Any doubt in this case?
No.
Let's think. Okay, so this was the relation between electric field and the electric potential. Okay, you can just note down this expression because we'll be using this in multiple cases. Okay,
Sure.
one more thing, whatever I have shown you in the case, I have taken my electric field as a varying electric field. Clear?
Oh, okay.
Okay, so you can assume if my electric field, for example, here, if your electric field goes as a function, let's say that it goes as a function of x, for example, the value of electric field comes out as E naught a times of x. You can directly put an integrate, right? But
Yes. Yes.
if it has a constant value E naught, you don't have to do anything, just keep it outside and integrate, like just to do whatever the distance you are moving. Okay, so it
Okay.
will work in both cases. Now, uh, now we can go with the electric field from potential. Okay, how I can figure out electric field from potential? If you see the relation is fine, we can calculate potential energy from electric field, right? But
Yes.
I want another thing. I want um, to calculate electric field from potential energy.
Okay.
Expression for electric field in terms of potential. So how we can do this part? Again, we'll be using the same method, but some experiment will be different. Okay. So I don't think you will be having doubt for this point,
Yeah.
right? Till now everything was clear, so we can also conclude that UF minus UI divided by Q equals to how much? This is, you can say, this minus E dot ds. I think it is
Yes.
clear.
Yes. Yes.
Okay. Okay. So now what I can do is, if you see carefully, I am having something. If I can rewrite this whole thing as V, right? Potential.
Yes.
Okay. So this is potential negative E dot ds.
Yeah.
Now what I can do, I can differentiate both sides. Is that clear?
Okay.
If I differentiate both sides, what will happen? This, okay. One more thing, I'll be differentiating with respect to ds. Okay. So when I differentiate this whole thing with respect to ds, what will happen? This integration will cancel, get removed. Understood?
Yes.
Okay. But I'm differentiating this with respect to ds, so it will become dv by ds. Make sense?
Yes.
Just a second. And a better, instead of direct, because there's a dot product, right? So clean that dot product also. Before differentiating, put that dot product because it's in a dot product. So yeah. V equals to this E cos theta of ds, and the angle between this is a constant thing, so I can keep that outside. Yeah. Cos theta E dot no, E is removed, right? I am just left with the magnitude part. Now I can differentiate it. Okay? If you differentiate it, you will be getting ds equals to E cos theta. Okay, so this is the formula. Yeah, one more thing, negative sign. Don't forget the negative sign. So
Yes.
finally, I can write this as E cos theta equals to negative of dv by ds.
Okay.
All right.
Yes.
Now, what is E cos theta? If I say what is E cos theta, so E cos theta is a component of E which is in the direction of ds. Is that clear?
Yes.
For example, my electric field is like this. Okay, and let's say I have moved till this direction. For example, I instead of in the previous figure, instead of moving from here to here, I am moving like this. Okay,
Okay.
so at this point, if I take any point, let's say this direction of electric field, it will be having two component. One is this, one is this. So you can see this is an invalid component, right?
Yes.
Or you can see what is my net displacement. Only this part is my net displacement. Can I see?
Which part I can't see?
Okay. For example, if this is my electric field, okay, and if I'm moving from here to here,
Uh-huh.
so what do you think? My ds will be this to this, or my net ds should be this only? Because look, if you see, if I'm taking this as my ds, there should be an electric field in this direction to which
Yeah.
I'll be evaluating, right?
Yes.
But there is no electric field. So what
No.
I can do is I can say I will take the one component, like if this was my electric field, I'll be taking this as a component. So this will become E of cos theta. Is that clear?
Yes.
So I can say this E cos theta is nothing but the electric field in the direction of displacement. Understood?
Yes.
Or in another sense, you can also say one thing, that if you want to say, okay, I'll be putting the net electric field, so then what you have to do is um, remove this part. Now, if you see carefully, what is my net displacement? Because what is my net displacement? Only this part is my net displacement, right?
Cos theta. Yes.
So I can also say that instead of E cos theta, I can say ds. It was ds, I can say net displacement is ds cos theta, right?
Yes.
So if you see carefully, if I take this cos theta downside, what I'm going to get, I'll be getting something like, remove it, cos theta. What is this? This is nothing but net displacement in the direction of electric field. Or if you want to write another form, okay, so if you want to put ds over here, it is nothing but electric field in the direction of displacement. Is that clear?
Clear.
Okay, so basically you should be clear with the things. Okay, you should be clear with the directions. If you am
Okay.
writing E cos theta, it means I have taken the component of electric field which is in the direction of displacement. Okay.
Yes.
If I'm taking net, if I'm taking net displacement over here, like net electric field over here, it means I'll be taking the displacement in the direction of electric field. Make
Yes.
sense? Okay. Okay, one more thing. Why I'm not taking total displacement. The reason is this displacement has two components. One is this direction, one is in this direction. Okay. If you see carefully, for this displacement, there's no electric field. It goes as a perpendicular. Okay, so this electric field doesn't provide any effect on this displacement. Is that clear?
Yes.
Okay, so this is the reason. We are not taking the perpendicular component, we are just going with the one component.
Yes.
You can write this. Let me check if I read these notes. Correction. Okay, this portion has been cut down, I think. Okay, not too much. I can paste it here. I can see this one. Leave it. Okay. Any doubt you have till now?
No.
Okay. I'll just try to print this. The page got cut. Okay, one more thing. Let's write the whatever we have calculated in terms of components. Okay. So
Okay.
how we can write it? Let's say this is minus dV, right? Is it?
Uh,
You know, this displacement can be in three different directions. Okay,
yes.
so what we can write it as dv equals to e times of dx plus e times of dy plus e times of dj. Okay,
Okay.
it means I am taking component ex with dx, ey with dy, ez with dz. Okay, now what is benefit of it? If you do this now, you don't have to take any cos theta or something. Okay, because when you will be calculating, let's say in this case, it will be having only this component ex and dx. Okay, so you will be getting value for this. For dy, you will be having dy also, but you won't be having ey. Okay, so it comes out 0. So this expression will go 0. For ez and dz, you don't have anything. Either you don't have ez, you don't have dz. Okay, so this expression will get 0. Understood?
Yes.
Okay, so wherever you have seen till now the displacement part, you can extend displacement as one more thing: x component plus y component plus j component, whatever. Like, you can write it as this: dx of I, dx of j plus dx of k. So any expression you have and you can see dot product, you can just provide dot product and you will calculate dx, dy, and dj. Okay.
Okay.
Alright, so remove this. And in partial terms, like how you can write electric field, so it will be minus partial dv by dx in the expression, and it is for y, it is nothing but dv by dy ez equals to minus dz equals to d. I think dv by dz. So this is for electric field, this is for potential. Clear?
Yes.
All right. So I'm giving you one problem. Try to solve. You try to solve this one. The question is saying Cartesian component, which means you have to calculate other like ex, ey, and ez. Okay. What happened?
Nothing, sir.
Okay, you're trying, right?
Yes. So we only have to differentiate, right?
Yeah, we only have to differentiate.
Yeah, I have done that.
Okay,
Hello.
so
Yeah,
should I solve this one?
I have done. So
Okay, you're done. Okay, so what is you are getting for EX?
y square minus 12x square.
Y square minus.
12x square.
Okay, I think you missed negative sign, right?
Oh yes, yes, you're right. You're right.
Okay. All right. So for EY, what you got?
Minus 2xy.
And EZ?
0.
Yeah, that's fine. Okay. So you can see in potential, we don't have any Z expression. It means the dependency of voltage, like voltage doesn't depend upon your Z coordinate, right? So we can say that your EZ component will get come out to be zero
Okay.
directly. Clear?
Yes.
All right. So the next thing which comes up for us to study is electric potential of spontaneous charge distribution. Clear?
Okay.
Okay. So first thing we can take as a charge conducting sphere. Okay, a solid conducting sphere which is having a radius r and will be having a total charge q.
So what
Okay.
is the topic?
Topic is basically will be going with spontaneous charge distribution.
Okay. Okay. Yes.
Okay. Here I can see spontaneous charge distribution. First thing which we are going to study is first thing which we are going to study is um, a charged conducting sphere. Okay, tell me the properties of a charged conducting sphere.
Uh, like in what sense?
Okay, a very simple thing. Conducting sphere is that it means first of all it will be a conducting nature, right? It
Yeah.
is charged. Okay,
Uh,
I didn't told you whether it is hollow or solid. So
yes.
either case you take because it is a conducting, all the charges will try to move outside. Means all the charges will present at the outside of the body. Is that clear?
Yes.
So for solving a conducting sphere, either I take solid case or either I take hollow case. The result will come out to be same. Is that fine?
Okay.
Yeah.
Yes.
So first, what we can take is we can take something. Okay. So let's make figure first, and we'll try to understand. Assume this is the figure, okay, and I have this, charges inside. I put charges inside. Let's say I'm taking solid case directly because hollow is you might know all the charges will at the surface. If I'm
Yeah.
taking a solid one also, so all the charges come out at the surface. Okay. So this
Okay.
is one thing I know. If I go outside, let's calculate for r greater than r. Okay,
Okay.
this is my radius. Mean to say r greater than r. Mean to say I'm trying to calculate potential at other points. Okay. So what it will be? What should be the value? I know one thing that what is potential dV by okay, what is potential outside? So potential is nothing but negative E dot ds, right?
Yes.
Okay. So what is electric field outside? K q divided by r square, and
Yes.
I am doing here dr. So can I say whatever I have written, it will come out nothing but k q divided by r.
Okay.
Okay. because if you integrate this, if you just integrate this one, you are going to get k q minus 1 by r. Okay, and you are going from this capital R to somewhere, some value. Is that clear?
Yes.
Okay, so we can say that whatever we are going to get, yeah. Okay, so to move this part, yeah. So this thing, this is the thing. So we can say potential we are going to get kq divided by r. Is that clear?
Okay. Yes.
Okay. If you are just at the surface, what value you are going to get?
KQ by R.
Kq by r. Okay. The whatever value we are going to get is kq. Okay. Yeah. Kq by capital. Or basically, you can put the values. Okay.
Yes.
Now, if you see carefully, I have okay. It can be written as greater than and equals to. Okay. The fun thing will come up when I'm going to get into the for r is less than capital R. This is important part. How important it is. Let's see. What do you think? What should be the exact value of it? Electric field. You know one thing that
For R less
change
than.
in yeah. Look one thing. You know that when I'm at the surface, okay, very surface, charge is just present at the surface. Surface mean to say surface has some width, right? So when okay, that's why somehow question got mixed. Okay, so when I'm saying I'm looking at the surface, what does that mean? I have this surface na, for this one. So I am my charges are present somewhere here. Okay, very surface. The mean to say the charges are not outside of the body, not very inside, just at the surface. Is that clear?
Yes.
So you know after this reason, you know the value of electric field. Okay,
Yes.
that is k q divided by r. But you don't know the value of electric field because if you could remember electric field inside the solid or hollow sphere, what was that?
KQ R square, capital R square
It
plus
was
small
zero,
r.
na?
So for inside. Yes.
Yeah, for inside it was zero in case of conducting.
Yes. Yes.
Okay, you could remember, right? So if I do the same method, I don't have any value inside, so I will be getting a potential is zero also. Is it?
Yes.
Okay, but it won't be the case. Why? Let's see. What is a potential? Potential is nothing but dV by ds, right?
Okay. Yeah.
It is equals to electric field.
Yes.
If you see, if I just at this point, if I just tell you what is electric field at this point, so what you will say? You will say electric field is zero. What you are going to say?
Okay.
Electric field is zero, right? At this point,
At which point?
yeah. Basically, this was surface. This is outside, but
Acha,
inside,
acha.
just
Okay.
inside the
Okay.
surface, electric field is zero, right? In this case,
Yeah. Yeah.
I can say electric field is zero.
Okay.
What does this expression says? dV by ds. It says the what is this basically? It means V final minus V initial divided by S final minus S initial. If I
Yes.
ask you what is S, I can say this was S initial. This point, whatever I am checking, it is S final. Is it?
Yes.
What is V here? It has some value. V surface. What is this? I want to calculate. So can I say this whole thing is nothing but zero?
Yes.
Basically, here your V is not here V didn't comes out to be zero. Here change in V comes out to be zero. Is it clear?
Yes.
If
Okay.
change comes out zero mean to say V final minus V initial. And because I am checking at just surface and just inside, it means whatever the value I had at the surface should be equals to BF. Basically
Yes.
inside, right? Inside. Let's write inside. So can I say potential inside or for potential at R should be equals to V surface?
Yes.
What is that? KQ divided by R.
Yeah.
Okay. Don't write it small r because we are in right now this. Okay, if you do small r, mean to say my potential depends upon distance. No, this is not the case. It is constant. Okay,
Okay.
potential inside the charge surface is constant. Mean to say, okay, understood this part how we comes up to the conclusion that potential inside the charged conducting sphere is zero.
So
Like it's
actually,
a
the
constant
it's
value.
because of the change of potential.
Yeah, it's
It
because of the
comes to be
changing
zero.
property of the potential. Okay, because I know change in potential depends upon electric field. But if
Yes.
electric field is zero, it means the change in potential comes out to be zero. Change
Yes.
doesn't mean that the value is actual zero. Change means whatever you had initial, it will be the final also. Okay.
Yes.
When I was at the outside, mean to say surface to outside. In that case, what happens? My electric field is changing. Okay, so that's why dV had some value. It was not equals to zero. So that's why when you are changing the position, you had a different value. But when you just try to go from here to here, what happened? dV comes out to zero in this case. Mean to say change is zero. Whatever you had at the very last point of what you can say meet, like this point is meeting at this surface, right? What is this point? Surface. What is this? Inside. Okay. Now inside means any point if you go. Okay, any point you give. If you take this point and this point, change in potential zero. Electric field here is zero. Like here is same. It means here we had Vs, right? So can I say all the point inside the sphere are going to have same potential value?
Yes.
Okay. So let's remove all the things. So in better sense, Vs V in. Okay. So dV by ds comes out to be 0 equals to E, not right, E equals to 0. Here your dV comes out to be 0. So V final minus V initial comes out 0. We are going from here to here. So what is this? V inside equals to Vi. Basically Vs comes out as how much? KQ divided by R. Clear?
Yes. Yes.
Okay. So this is one thing. Okay. So look, yeah, continuous charge distribution. So by now we have completed continuous charge distribution for conducting sphere and okay, for conducting sphere we have completed both cases. Okay, R is greater than this and R is less than this. Okay, if
Yes.
you could remember in this case, what was the electric field value which you used to get?
KQ by R square plus any R. I think it was something
KQ
which
by
was
R square, general KQ by R square, right? This was the
wasn't
thing
it,
when you go distance, R was increasing.
wasn't it R plus R whole to the power 3 by 2?
No, no. Okay, wait. You are confusing with this, right? KQ x divided by R is cube, I think,
No,
right?
R plus R, no, capital R plus small r raised to power 3 by 2.
This was the value, but for not this thing, it was in the case of okay, wait, which value you are telling?
I'll have to check what I'm talking about.
I think you have confused in some values.
Yes.
Okay, just a second, let me go back. Must be PPT should be there. Electric
Okay,
flux over
I'm telling electric field due to uniformly charged ring.
uniformly charged.
Ring.
Okay, okay, you are okay. Yeah, that is for the ring. Okay, it is a sphere. Okay, in
Yeah, yeah.
ring we were calculating like this, right?
Mm. Yes, yes, yes.
Don't
I
confuse
got
with that.
confused.
No problem. Yeah. So this was here, and electric field in this case was how much? Zero. Okay. Now,
Yes.
how your graph will look like? If you see, if I say what is my electric field graph looks like? Electric field looks like is this is your E. Okay, this was your distance. So till distance R, you had zero electric field. At sudden, you had some value of electric field. Okay, and after this, it starts decreasing, right?
Yes.
How your potential will look like in this case? It had some constant value from very start, right?
Yeah.
Okay, till distance r, it had constant value of r. What was this constant value? K q divided by capital R.
Yes.
After this, because distance is increasing, it starts decreasing. But how it is decreasing? It is decreasing like this. Clear?
Okay. Yes.
So this is the thing. Or if I have to show it in the form of circle itself, so how I will show? This is the sphere. Okay. I can make this sphere. This is the center. This is the radius r. So let's plot a graph over here. This is the line. Okay. So for electric field, what was the value? Till from zero, from very center to this r, you don't had any value, right?
Yeah.
But at a certain moment, you had some value from here,
Yes.
here to this side, and there to that side.
Yes.
Okay. This is for what? Electric field. Okay. What I will do, I can just paste the. Okay, how to copy this part? Okay, I'll just create another. This was for electric field. Okay. Let's write E over here. E and R. We have minus R. Okay. Now for your potential, how it will look like? This was the sphere. Okay. This was the boundary it had. This kind of boundary it had. This was very center. Here you had to calculate V. Okay, at from in this region, from there to there, you had a constant value, right?
Yes.
So this is a constant value. After this, whatever the value was, it starts decreasing. So this is
Okay.
the difference you'll be getting here. Okay, so we can call it as this by this, and this is your center point. This is your R. This is your R. You can see this graph contains both cases, from inside to outside. Okay, if you have to see, okay, this I'm inside 0 to this capital R, capital R. In the negative sense, minus R. Okay, fine.
Okay.
Yeah. So this is all for today's class. In the next class, I'll be covering from the non-conducting sphere. Okay.
Okay.
Yeah. So if you have any doubt, you can let me know, or you can just end the session from you. Like you can just leave the session.
Hmm. Thank you, sir. Bye, sir.
Okay. Yeah. Goodbye.